Good evening, friends. Welcome to the session. So we were doing domain analytics and we were looking at legal and law analytics program. This is an ongoing session and today we'll be seeing unsupervised learning using clustering techniques like K-means. Okay, so let us discuss today's agenda. So we'll be seeing unsupervised learning. What is unsupervised learning? What is clustering? What is K-means clustering? What are the advantages of K-means clustering? What are the limitations? And what are other key concepts in K-means clustering? And also we'll be seeing few use cases. So let us see. So first of all, let us understand what is an unsupervised learning. Okay. Unsupervised learning. So unsupervised learning is based on the property where our output value is not known. Okay, so here we are given a data set, okay, or we are taking this data set and from this we are trying to find some insights, okay, or we are trying to find, we can say, hidden patterns or trends that was that you could not find earlier. Okay, so hidden patterns and trends we try to find, and based on this property we try to form groups or clusters of records together. So let's see how this is working. So we are given a historical data. We are having this historical data. We apply some machine learning algorithms, some machine learning techniques on this data, and we extracted some rules and patterns. So this is the underlying idea of unsupervised learning. From a historical data using machine learning, we are extracting some rules or patterns. Now these rules and patterns again, this can be used, okay, to predict under which cluster or under which group a new data would fall. Okay, using this rules and patterns, we can predict the outcome for this new data. So this is the underlying idea of unsupervised learning. So let us see. Let me clear the screen. So the general idea, let us go through this once. Unsupervised learning. It is a machine learning technique, okay, in which models are not supervised using a training data set. Okay, so we do not, so generally in supervised learning, what we do, we are having a training set. Using this, we supervise and form mathematical equation. Using this mathematical equation again, we will, on the test data set, we can do prediction. But here no training data set is there. We are having just a data set from which we try to find insights or patterns. Now instead you can see here, model themselves find hidden patterns and insights from the given data. Okay, the ML models find hidden patterns or insights in the data. Now, this can be compared to learning, which takes place in human brain while learning new things. When a human brain learns new things, okay, it tries to find a relation between this new thing and some other old thing. So here also we try to do something like that. Now the goal of unsupervised learning is to find the underlying structure of the data set. Okay, hidden or natural groups in the data set. It tries to find. Okay, and group that data according to similarities and represent that data set in a compressed format. Okay, so basically what we are doing, we are forming clusters, and we can use these clusters or groups as an individual data set, and we could do further uh, further analysis on this individual. Now this resultant group and clusters will have low variance. So basically this is a minimization technique. Minimization technique. Okay, in which we minimize variation or variance. Variance. How do we minimize variance? So what happens? We are forming clusters. So we make sure that this cluster is tightly formed. Okay, tightly means the points in this cluster will be very near to each other. Only then we can say that yeah, variation is very less or having a low variance. Because variance is nothing but it is the distance from centroid or the center mean value, you can say. Okay, so as close as the point is, less will be the variance. Okay, let's go to the next slide. So here we can see how this occurs. So we are having unlabeled data. So we don't know means the output of these labels. Okay, unlabeled data we are having. By using our algorithm, clustering algorithm, we will now cluster it and label the data. Okay, our main thing we do is give a logical name to the clusters. Okay, we try to give a logical name to the clusters. So not only we form clusters, we try to find some inference from these clusters. We can use these clusters again to do further analysis. Okay, and why is it called K means? Let me also tell you. K means, okay, K is the number of clusters which we want to form. Clusters we form. This has to be decided beforehand. Okay, this has to be decided before Okay, first step is decision what k value should be. This should be our first decision. Once this is done, that many centroids randomly chosen in our data set. That many centroids are randomly chosen in the data set. Okay. Once this centroids are chosen, next we start clustering. So we find the closest point to that centroid, closest point to that centroid. Once we find this, we will cluster them both. And once it is clustered, now the centroid will shift. It will be the arithmetic mean of these 2 points, of 2 points. Again, this will be repeated. Again, we'll find the distance of all points from this centroid, newly made centroid. And again, it will be clustered. Again, the centroid will change. So this, because this mean value or centroid keeps on changing, this is known as k-means technique. Okay, so let's see. Okay, what is k-means? Let's see. So k-means is one of such unsupervised learning method that aims to group similar data points in clusters. What does similar data point mean? Similar data points. Okay. So how can we know if 2 data points are similar? Okay. Suppose we are having here 1 point, here 1 point, here 1 point. Okay. So what we will do? We will measure the distance between these 2. Now this distance we can measure using various formulas. This distance can be measured using Euclidean distance. Can also be found out using Manhattan distance. Can also be found out using Mahalanobis distance. Many methods, many more methods are there. Okay, but we generally use Euclidean. If the need be, we can use any other method also, it is okay. Okay, so Euclidean distance, let me tell you the formula. If we are having a point here and we are having a point here, suppose this point is having these coordinates x1, x2, x3, suppose, and this point has p1, p2, p3. So the distance between these 2 can be x1 minus p1 whole square plus x2 minus p2 whole square minus x3 minus p3 whole square and whole root over. So this is the formula for Euclidean distance. Similarly, we are having Manhattan, Mahalanobis. Formulas are different, but yeah, if you are doing Euclidean, you should do Euclidean for all the distance measure. If you are doing Manhattan, then you should perform Manhattan distance on all the points, and Mahalanobis, then Mahalanobis on all the points. So this is how we calculate the similarity between 2 data points. Okay, once this is done, we will cluster the data into different groups. Okay, and this convenient way to discover categories of groups in unlabeled data set on its own without the need of any training. Okay, this k-means clustering gives us this facility. Okay, it gives us a convenient way to discover categories of groups in unlabeled data set without any supervision. Okay, next. Then k-means is also a centroid based algorithm. Okay, its centroid keeps on jumping from one uh, place or one place to another place. So centroid will keep on changing as we form cluster. So you can see it is a centroid based algorithm where each cluster is associated with a centroid. The main aim of this algorithm is to minimize the sum of distances between the data point and their corresponding clusters. Okay, so we want this cluster to be as tight as possible. And also there is one more thing. It should be as far as possible from the other cluster. Now, what are the steps involved? Let us see. So steps involved in k-means. So first of all, we must decide the value of k. Now, how can we decide the value of k? What is the parameter for deciding this k value? How can we know what k value should we choose so that we will get a correct clustering result? So we have been given a formula which is root over of n by 2. Okay, this is an old formula and this will work only for small data set. Because if we see, if it is suppose 18 by 2, root is 9. So we are seeing that this is 3. So 3 cluster can be easily formed. Now suppose we are having 200, okay, 200 data points, 200 records. 200 by 2 is 100, root over is 10. So 10 clusters, okay, it is a very large number. And we don't have just 200, we have 2 lakh records. 20 lakh records, suppose we are having. This will be how much? 1000 cluster. Do you think it is good to have these many clusters? It is not. Okay. So this is as with the advent of increase in data, we don't follow this rule anymore. So there is one more thing we can do. Okay. We can ask the subject matter expert, okay, how much cluster is needed for this project. Okay, we can do this as the subject matter expert. Okay, there is one more method. It is based on the usage of scree plot or elbow plot. Okay, so we'll talk about this, but let us first know about. We can also do this using WSS and BSS. So WSS is nothing but within sum of square, and BSS is known as between sum of square. So what is this WSS? What is this BSS? Let us know this first. So this WSS is known as within sum of squares. Okay. And this BSS is known as between sum of squares. This within sum of squares measures the distance within a cluster. Okay, distance of all data points from the mean value within sum of square. Okay, summation of x minus centroid square. Basically variance formula, similar to variance formula we are getting this. So within sum of square, should be as low as possible. If it is not lower than BSS, then this point will jump to the other cluster. Okay. Similarly, BSS should be as high as possible. If it is high, meaning, so WSS is inside a cluster distance, and BSS is distance from cluster to a different. So if a data point is here, so we'll measure this distance from this centroid to this centroid. If this centroid is less, BSS is less than this side, so this point will jump to this cluster. Okay, so we measure that. Now this WSS and BSS calculation. From this WSS calculation, we can also find total within sum of square, which is the sum of square or within sum of square of all clusters together. Okay. So we will find this. Okay. For different value of k, we will find the total within sum of square for different value of k. Different value of k. Okay. Then we will just give me. Okay, let me just show you here. Then we will plot it. Different value of, sorry. Then we'll plot different value of k. K is here 1, 2, 3, 4, 5, 6, like that. And here we have different value of TWSS, total within sum of square. So which values we find? Okay, the values, TWSS values, which we found for different values of this k, we are going to plot it. Okay, so the plot will be something like this. It will start at a higher end, but it will fall down bit by bit. So like this. So sometimes you may see this kind of, not this kind. Wait, let me. This kind of plot you might be able to see. Okay. So wherever we find this prominent bend in our slope or change in slope, we will take that point as our number of clusters. So it will not be a bend between two numbers. It will always be a bend at one of the k values only. So we will take that k value as our cluster. Okay. So now we know the number of k. So our first step is done. Number of, before this we are having, this is step 0. Determine the k value. Determine the k value. Okay, once this k value is known, next we will initialize the centroids. We'll initialize k centroids. So if k value is 2, we'll initialize 2 centroids. Okay, this is randomly done. Now for each sample in the set of samples, we will assign a point, a data point, which is the closest to the k or to the centroid based on Euclidean distance, as we were discussing. Okay, then for each cluster in the set of cluster, we will again recalculate the cluster centroid. Okay, we will again calculate the centroid after clustering, and this will be the new centroid of this cluster. Now next we will be repeating these 2 steps again and again until a stopping criterion is fulfilled. Okay. Once this is done, next we will find the variance of each cluster and we'll sum it. And this will be again, done until we find the best cluster. These 5 steps will be again and again done with different initialization point. Okay. So once if you run k-means, okay, it will give some value. Again, if you run, you'll see it will give a different value unless you have set a random state. If you set a random state, then you'll get a same solution. That means your initialization will be done always in the same. So this main thing is initialization. If this is done correctly, k-means will be having good results. Okay, so let us learn what are the advantages of k-means clustering. So this k-means algorithm is used to group unlabeled data sets into cluster based on similar attributes. Okay. Now this k-means is also used. It is the most used clustering method because it is computationally inexpensive. With this, we can also scale, okay, large data into small clusters, and we can use these clusters for further analysis. And it is also appropriate when the number of clusters is known. Okay, it is the best method when we know how many clusters we need, and it is very fast. Okay, speed is one of the advantages of k-means clustering. Okay, so these are few advantages of k-means clustering. Now let us learn what are the limitations with k-means clustering. The limitations are number of clusters are needed to be chosen upfront. Okay, it is not like after we did some analysis, then we will choose the k value. Then is after we have done the algorithm, we'll choose a k value. No, here we need to choose upfront a k value. Once this is done, k value, then we can go along with our clustering technique. But if this k value is not correctly chosen, we will not get a good clustering. Okay, and if we don't get a good clustering, we will not be able to logically explain the clusters. Okay, so the main thing here is to logically explain the cluster or define the cluster. If this cannot be done, then the clustering is not good. Now, outliers, okay, can have a strong influence on the result. Okay, outliers are discouraged. If we are having outliers in our data set, it is better to treat it. Okay, it is better to treat the outliers first, then go for clustering. Otherwise, we might get a result which might not be conforming with the data. Now, initialization. We have to decide the initialization point. If this is not correctly chosen, okay, initial data points are not correctly chosen, then our cluster form will be not good. We will not be able to again give a logical name. We will not be able to explain why this cluster has formed, why this cluster with these properties are there. Okay. Next, it doesn't also cluster well with clusters of varying size and density. If we are having, suppose, a property of a few people, and in the same data set we are having properties of a large number of people, it will not be able to do this clustering. Okay, some of the data points will be here. The clustering will not be good. Okay, it will not give us good result if we are having a varying sizes and density of similar points. Now let us learn what are the few key concepts of k-means clustering. So k-means clustering, for stability, we should run the k-means clustering multiple times. Okay, and each run is known as an iteration. Okay, it is known as an iteration, and this iteration you can also choose different value of k. Okay, now what this will do, this will address if we are having multiple we are having minima values, local minima values. So what is a local minima? So as we know, this is a minimization technique. So let me show you. As we know, this is a minimization technique. Okay, suppose we are having something like this. So minimization basically is finding a minimal point. Minimal point in a graph will be these points. Okay, the point which is at the lowest point, and then we have a rise. So these points are minimum point. Suppose I'm having a point like this. I'm having a graph like this. Okay, let it be. So this point and this point, both are minimum. Both are minimum. But we can see that minimum point is this one. This is the minimum point. Now this minimum point will be a global minimum. Global minimum. This point will be a local minimum. This is a minimum also, but this is a local one. So what will happen? Suppose we are running our algorithm and we are here. So we are coming, we are minimizing, and we reach here. Okay, after reaching here, when we see this side, this is increasing. So we'll say this is the minimum point. If we have initialized this, okay, if we have initialized here, then we will check for minimization, and this is where we'll find. Okay, but if we just run it once and we are starting here, we will never reach this point. Global minima will never be reached. So it is better to have multiple runs. Okay, it is better to have multiple runs so that we reach our this goal or this global minimum point. Okay, now another another problem might occur when we are having a point which keeps oscillating between two clusters. Okay, suppose I am having a cluster here, I am having another cluster here, and we are having a data point here. So this has a a centroid here, and this has a centroid here. Now suppose we measure the distance. We measure the distance from centroid. So we see after measuring that it is closer to this. So it goes inside this cluster. Now this, suppose the centroid shifts here. Now again, the distance of this point from here to this centroid and here to this centroid, we again measure and we find that this is now coming under this. Okay. So what will happen in this case? And suppose after merging with this, we are having this here. Okay. The centroid shifts here. Again, this will jump to this. Okay. It keeps on jumping infinitely. So if this is the case, so what we can do? Okay. You can see a data point might keep oscillating between two clusters in each of the runs, and algorithm will enter infinite loop. So we can address this by choosing a convergence criteria or by specifying maximum number of iteration. So this is one of the iteration, then this is another iteration. So number of iteration or number of jumps we can limit it. We'll say only 30 times should be our max iteration. Then 30 times it will jump, and wherever, in whichever cluster it is, it will stop there. Okay. So there are other convergence criteria also. Like we can also set that this distance, how much it moves, okay, will set a threshold value. If our center moves less than this threshold value, we'll say that that is the end of our cluster. Okay. So this way also we can do it. Okay, so we just I'll read through this. Convergence criteria is to stop when a cluster centroid moves less than a certain percentage of smallest distance between any of the centroids. Okay. Then also we need to compare between cluster variation and within cluster variation. I told you. Okay, this should be more. This should be less. If this is not the case, then our clustering is not correctly done. Okay, and here the objective function is sum of squared errors. We are trying to minimize this. Minimize the sum of squared errors. Okay, or variance, we can say. We are trying to minimize this. Okay, so let us look at some of the use cases for legal studies. Okay, legal analytics. So first use case we are saying is case summary extraction. So we are having loads of, legal case documents. We are having loads of legal case documents. Okay, so from this legal case documents, we need to find the case summary, or you can say topics of the case. Suppose this is what we want to find out. Okay, so what to do? So there are various, approaches already there. So let me tell you something about those approaches first. Then we'll move on to this, what we are doing here. Okay, let me take black color. Just a second. Okay. So what are the existing approaches? Let us see. So this is a case of text summarization, you can say. Okay, we are trying to find the case summary. So this is a case of text summarization. And this is summarization of legal documents. So it is a legal domain. Text summarization in legal domain, you can say. And in this, the earliest work is the fast legal expert fast legal expert consultant. Okay, or in short, it was known as flex econ. Okay, it was developed in 1991 by Gelbart and Smith. Okay, and it is a keyword based it is a keyword based algorithm, and it does referencing against a large database. Okay, large database of terms to find importance in our text, whichever text we are looking for. Okay, what are the important parts of our text we can find using this. Important, we can say regions of text. Okay, now this has, we can say this is the starting point. Okay, it can be said as the starting point of text summarization in legal domain. Okay, so one is lexicon. Again, so let us discuss a few more. So lexicon was the first one. We are also having something known as Solomon. Okay, this is based on cosine similarity. It finds similarity using cosine similarity. Okay, it can be taken as an alternative to lexicon. Okay, later we also found sum and let sum. Okay, these were based on thematic structures. Okay, later we also had something known as lexa. So it used something known as RDR. RDR is ripple down rules. Okay. It allows the domain or legal domain experts to evaluate sentences, evaluate the sentence selections, and it makes them agree or disagree with the selections. Okay. Still, we are having a lot of automatic, text summarization tools, but still some problems arises during summarization. So some of the text summarization tools we are having, let me name them. Case summarizer, we are having one. We are also having something known as summarist. We are having something known as SMMRY. Okay, and many more are there. But the problem still remains. Okay, this summarization is a big problem. So let us see what approaches we can follow. Okay, so we are having this legal case document. We will use first some pre-processing techniques. Okay, text data. It is basically a text data, so we'll use some pre-processing techniques like tokenization, lemmatization, removal of stop words and punctuation. After this is done, we will form a term document matrix using this TF-IDF. Once this is also done, we will then cluster it. So we'll be using here k-means to cluster it. Once this is done, then we can extract the topics, okay, or summaries from this using again TF-IDF and title summary score. Okay, and based on this title summary score, we will be taking the top ranking topics of each cluster, and these will form our case summaries. Okay, so let me go quickly to the next use case. It is identification of arguments. Okay, so this cluster algorithms can be applied to argumentative sentences in order to identify arguments. This argumentative sentence may not belong to one specific argument. Okay, they might be part of another argument. So this is a problem. So this can be addressed by fuzzy C-means algorithm. Okay, this is also clustering algorithm. So if we see just the means flow of how this works. So we are having argumentative sentences. We apply some of the features like word to vec, sentence closeness, n-gram, combined features, okay, to classify it. Okay, so these are feature extraction methods. We're extracting features, pre-processing and feature extraction is done here. After this is done, then we are classifying this using fuzzy clustering algorithm. Okay, we are making groups in that using this. Once this is done, then we can start building argumentative building. Okay, which sentence will form arguments? Which two sentences can form arguments? We will check. Okay. So this was another use case. So quickly let us go to the coding part. Okay, just okay, so let us see. We are seeing K means in US crime data. Okay, so we are doing this in a structured data. So we can see here we are having crimes committed in the year 1973. This data is again divided into few parts like murder, assault, rape, and it shows the number of arrests in each crime per 10,000 residents, okay, in each of the 50 states. So let's see what we are doing here. So we are importing the basic libraries and also the data set. Okay, so this is a snippet of this data set. We are having a state, then urban population, number of murder cases, number of assaults, number of rapes, and total number of crimes. Sorry, total number of arrests, not crimes. Total number of arrests. Okay, so we are doing some of the EDA here. So here we can see the total arrests versus population. Okay, so this is the urban population, red one, and total arrests. Okay, this is total urban population, but in just multiply it with 1000K more, sorry, 100K more. That will be the population. And this is the real number of arrests. So we can see Florida has the most number of arrests, followed by North Carolina. Okay, so the lowest number of arrests you can see is in Wisconsin. Sorry, not Wisconsin, North Dakota. This one. Okay. Similarly, we can see here different crimes. Okay, so we can see assault is the most prevalent crime in all the states. Okay, let's find the number of clusters. So I'm drawing this tree plot, elbow plot, to determine what will be the number of K. Okay, from this value, okay, what will be the number of K? So we have taken this K value to be 4. Okay, and we are doing K means on this. On doing K means, we found that we found these values. So let me also sorry, here we are having K means 4. So we are having these many. Sorry, clustering is not done. Just a second. This is the number of clusters formed 0, 1, 2, 3. So total number of clusters formed is 3. And this we are comparing the urban population to the total arrests. Okay. So this shows the total arrest. This shows the urban population. So we can see when we are having a low urban a low arrest, we can see it is spread over the data. But a higher urban population, we can see a little more number of arrests is there. And here also, we can see a more higher number of population is here, urban population. And here the highest arrest we can see here. Similarly, in this, we are looking at murder and assault. So we can see murder when it is low, assault is also low. So there is you can say, linear relationship. As this number of murders are growing, assaults are also growing. Okay. So we can see in 0th cluster, most number of murder victims are there. Okay. So then so now analyzing the two variables, we can see a clear connection between them. So you can see a linear relationship between them. So it shows higher murder rate in state go hand in hand with higher assault rates. Okay. And the second graph also shows that center of the four cluster here, you can see center of the clusters are on a nearly straight line. The clarity of the cluster is satisfactory, although we are having some outliers. Okay, so we can see this. If we are analyzing murder and rape, so here also we can see a linear trend, nearly linear trend we are having, but clusters are not that much defined. Okay, we are having mix up. So if we are doing analysis, okay, there is much more spread in the data if we are comparing it with murders and assault. Okay, and we can see also some correlation between the two, but low murder rates in the state also we can see is low number of rapes is also there. Okay, but for higher number of rapes we can see murders is low and high as well, both. Okay, let's check assault and rape. So this also we can see it is of similar nature to this murder and rape. Okay, so let's just go to the conclusion. Okay, so if we are considering everything, okay, if we are considering everything, then we can see that this crimes are not that much dependent on our urban population. So we can see different we are having, but so number of urban population, our crime rate is not increasing. So we cannot say that crime rate goes hand in hand with urban population. Okay, but yeah, different crimes here we can see are having a linear relationship, nearly linear relationship, or weak linear or weak positively linear relationship we can see. Okay, so if we want to draw conclusion, we can say there is no clear conclusive difference between the four clusters if we are basing that on the urban population. So we can say a large urban population does not automatically lead to higher crime rate. If we are taking the example of Hawaii, you can see Hawaii, where it is. Here. So you can see it has the highest. So it doesn't mean that, it is having the highest urban population, we can see. But if we see the crime rate, it is 45th. Okay. So we cannot say that this urban population, if we are having a higher urban population, we will have a higher crime rate. And we can see North Carolina, it has the highest crime rate. Okay, you can see North Carolina in this crime rate, it is the highest, second highest, but it doesn't have that much urban population. Okay, so we cannot find any correlation between urban population and crime rate. But if we want to dig deeper, then we might also find that due to socio-economic reason or demographic casualties, okay, this, these crimes are occurring. But we will have to find this. Okay, but in some, type of cases, we can see clear correlation between certain crime types, like we saw murder and assault. Okay, murder and assault. We also saw between murder, rape, assault and rape. Okay, so we could find some correlation between them, but this is needed to be investigated further to draw, clear conclusions on this data. Okay, friends. So that will be all from my side. Okay. This was K-means. We'll meet again tomorrow with classification algorithm. So we'll see that tomorrow. Thank you, everyone. Have a good day.